Welcome, everyone. Thank you for joining us for today's webinar, What to Know About Batteries and Battery Energy Storage Systems Hazards, presented by Gabriel Shelton. At BakerRisk, our mission is to manage hazards and risks through high-value services, products, and research. We achieve this mission through 5 specific areas: incident investigation, loss prevention, testing and research, risk management, and the BakerRisk Learning Center. We invite you to visit our website to learn more about BakerRisk. Now, for today's webinar, we have posted links to content related to our webinar subject. We invite you to explore BakerRisk published papers, previous webinars, and BakerRisk videos. Second, we want to respond to your questions following this webinar. Please type questions into the Q&A box in the Zoom control panel, and our presenter will respond to the questions. Finally, at the close of our webinar today, please provide feedback by responding to our survey. For today's webinar, we are excited to welcome Gabriel Shelton. Gabriel leads the Battery Hazard BESS initiatives for BakerRisk's Sustainable Energy Risk Management Services, and he is an accomplished structural engineer with 15 years of experience in the design of blast-resistant structures. Now, without further ado, I will turn the time over to Gabriel.
Good morning. Thank you for that introduction, Naomi. I'm going to give just sort of a brief overview and a background for the content of this presentation. So basically, we're going to go over what types of things can cause battery failures. How often do those battery failures occur? If they fail, can you mitigate those hazards? If you can't mitigate, what are the consequences? Whether you can design structures to contain the battery hazards consequences, and what is the loss impact if these failures escalate? I want to recognize my team members. So we have a team of various backgrounds and locations that are on our battery BESS hazards team. So Dr. Sean Berg is here in our San Antonio office, and he's a primary person in our materials lab. Dr. Woon Wong is a process safety consultant in our Los Angeles office. Rashawn Sebastian is a fire protection engineer located out of our Toronto office. Dr. Anibal Morones is a blast effects engineer. He's also here in San Antonio. Myself, I'm a structural engineer, and I'm also located here in San Antonio. And then Roger Stokes is a process safety and insurance risk consultant out of our Chester, UK office. So this presentation is largely borrows from a series of white papers, a 6-part series that we wrote recently in the last year or so, and is available to you all to download from our website. And it's all about battery hazards. And so Sean wrote a paper about battery failure analysis and characterization of failure types. Dr. Wong wrote about a paper about the frequency of battery failures. Rashawn Sebastian, his paper is basically about fire mitigation methods for lithium-ion BESS. Dr. Anibal Morones, his paper has to do with sort of quantifying the flammable hazards related to BESS failures. My paper has to do with the evaluation, design of structures to contain those hazards. And then Roger Stokes' paper is kind of an overview of all those papers, as well as sort of the risk management considerations. So I believe Naomi's going to post a link to where you can download those papers on our website. And I encourage you guys to do so if you would like a little bit more technical depth and some nice references to where you can find more information about. So having said that, I want to just sort of state that this is going to be kind of a high level discussion of these things. And really, if you take anything away from this presentation today, I want you to take away that we as BakerRisk or the industry can use sort of existing and industry accepted methods to quantify hazards and mitigate those hazards for something that is relatively new, which is lithium ion battery hazards and BESS hazards. So a little bit of background. Basically, what is a battery and a BESS? And I have a habit of kind of using these interchangeably, but a battery is what you think of. It's a container that has cells that store electrochemical energy that can be converted into electricity and used as a source of power. So you think of the battery in your phone or a typical battery that you put in your remote control. And so what's a BESS? So a battery energy storage system, or BESS, is a really large battery. And those are typically associated with either renewable energy sources such as solar panel farms or wind farms, where we need to sort of modulate the supply of that and store some so that we have like a steady supply. And those are basically large battery packs that are consist of actual small battery cells that can be packed into modules. Those modules are stored in rack systems, and then the racks are all put into containers. And those containers are in an array like you see here in the left photo, where and they're either on site, and some of these are just on the grid that, for situations where they want battery backup. So what are we talking about in numbers? So basically, this is a kind of an older, outdated chart, but it's from 2020, and it's showing estimates for 2021, 22, 23. And it's basically forecasting how many of these BESS systems are going to come online down the road. So you can see that it's increasing sort of at a great rate. And so while that's happening, we're also seeing a lot of incidents. So this is a reference from the EPRI database, and you can see that we've had 7 or so major incidents in 2022 and a few here from 21. And one thing I'd like to point out is this: we have 2 of these at this Moss Landing site in California. And so those are the same site that had 2 major incidents within a few months of each other. And I think this is actually one of the largest sites in the US, if not the world. So that's one thing that's sort of interesting. Another thing is that if you sort of go through, and the database for this is nice because it links to news articles and what have you. But anecdotally, you can see that the industry and first responders are sort of learning from these recent experiences in how they address these hazards and respond to them. So what can cause battery failure? So this section is basically going to be a little bit about how we can look at a battery that's failed, or look at and use forensic techniques to figure out what caused a battery to fail. And so this is based on Sean Berg's paper. And so let's get into this. So basically, batteries can fail in several different ways. You can have abusive operation, where maybe you're charging or discharging a battery too quickly, or overcharging it. You can have physical damage, like you could drop a battery or puncture a battery or have some other sort of physical impact to that battery. And then defects in the way the battery is made, such as the design itself or the materials that went into that battery, or even the manufacturing process itself can lead to defects that can cause failure. So these failures, the causes basically all sort of segue into thermal runaway. And that thermal runaway, and we're going to get into that, can result in either explosion, a fire, or a release of toxic gases. So what is thermal runaway? Basically, it's an uncontrolled chain of exothermic reactions that produce heat, and that heat then causes further damage to the battery and increases the temperature of the battery, causing more damage. And in large scale BESSs, these thermal runaway events can cascade from cell to cell, from throughout an entire module to the next module, and through the whole rack, and consume the entire BESS enclosure. And here's a photograph from an event in Marpool, Australia, where it was able to cascade over to an adjacent BESS enclosure. And basically all lithium ion batteries are susceptible to this type of failure. So I've got a nice video here that I think shows like the heat propagation, and not only the heat coming from a battery that's failed, but the propagation from cell to cell. So let's watch that. Okay, so I think that gets the picture across. So how do we investigate these? So it's important to determine why a failure happened. So one, we want to try to make sure or do what we can to prevent future events from occurring. A lot of times we do failure analysis in support of an insurance claim or litigation having to do with an incident. And there's some burdens, and I'm not sure exactly what these are, but to report to the regulatory agencies any findings. So basically, it's important in an investigation to have a rapid response and to properly preserve the site and the evidence to make sure that you have an accurate and thorough investigation. As part of that investigation, you're going to review the data, collect information. You could use like video or drone footage, and then infrared thermography, if you still have a hot scene, can also be helpful. It's important to identify the origin or where the thermal runaway began, and heat mapping can be useful to do that. So basically, we want to use a methodical approach, mapping the cause and try to find the one cause or the multiple causes that contributed to the event, and establish a timeline and sequence. And this is just a nice photograph of from a scanning electron microscope. It shows swelling in a battery casing that due to the overcharging of a battery. So what kind of techniques do we have? And I'm not going to go into, I'm going to try to stay at high level, but basically we have techniques that we can use that are non-destructive, and such as, microscopes and computed tomography. We can look at different things under different kinds of microscopes and sort of understand, the metallography or what's going on in the welds, the casings. We can use chemical analysis, structural characterization using various tools. We can look at the electrochemistry, and then we can compare a damaged battery to an exemplar battery. Talk a little bit about a case study, some images. So this was for a battery where the manufacturer asked us to evaluate some cells. So we opened the cells. These are some documentation of opening the cell. We characterized the materials, and we found some issues. One, the capacity of the battery was lower than rated. The chemistry of the cathode is not what was supposed to be there. It was lithium, carbon oxide versus nickel manganese carbon oxide. The current had a discharge drop off, which is probably caused by that material, the wrong material in the cathode. And in the housing, we found some sort of structural defects around the welds. So that's just one of the quick case study of the type of work we do in our forensics lab. So how often do battery failures occur? Now, this one's kind of a tricky one. So there's methods, empirical methods out there for electronic equipment that exist that sort of allow you to calculate, what a failure rate would be sort of in the early stages of a component, in the later stages of a component, and you can sort of develop a curve to predict what the failure rate will be over time. But BESS components may not or probably don't follow similar failure rates over time. Another thing is that the data set isn't large enough for us to understand what those trends are. And this is one, the fact that they don't follow the trends may be affected by several factors, such as the location, the climate, but load requirements and other factors, sort of like what is the use of the battery. And some other confounding issues is that, the battery technology designs are evolving very quickly. We're constantly having sort of higher discharge rates, higher energy density, longer life, and lower cost. And it's hard to find the data basically because there's so many different types of lithium ion batteries, so many people making them, different uses for those batteries, and the manufacturers don't really want to give that information out to everybody, and they're really the ones who would have that. And so there's some other issues that there are a lot of data being captured by various organizations, but in our research we found that the formats aren't really standardized. The types of data that's being collected varies. So whether it's abuse testing or standard use of batteries, that sort of thing. But the good news is we're learning from incidents through accident investigations. And, I have to plug that BakerRisk does a lot of this type of accident investigations. And the reliability of these batteries is constantly improving. So industry's learning from battery failures, but it's really a challenging thing to sort of quantify failure frequency for those reasons that we stated. And that means that trying to understand risk is very challenging. So if the batteries fail, can we mitigate these hazards? So this is a section that's basically talking about mitigating the fires that start from these battery failures. So one of the challenges with thermal runaway is that it's really challenging to stop a thermal runaway because lithium ion batteries have everything that's needed to cause a fire. So you've got your fuel, your heat, and your oxygen supply. And you also have the hazard of the electropotential or the electricity aspect of it. So that means it's a high risk for first responders to go in there and try to fight a fire. And also the fact that these BESS modular enclosures have so much equipment packed into them, it means that they can propagate quickly, but also it's kind of hard to get to the fire. And here's another photo showing that battery pack in Australia. So this is sort of a diagrammatic drawing of how heat propagation works, and it sort of shows the cells, modules, racks, and the whole BESS. And so, the original heat that causes or initiates the fire could happen in any given cell, just due to the operation of the cell. There's heat present, and some defect or something has caused a breach of the cell or something that starts a fire. But then once a fire is started in a single cell, it's as we saw in the video before, it's very straightforward for it to propagate to adjacent cells, and then once a module has been taken out, consumed, then propagation from module to module, and then the entire rack and the neighboring racks. And as we saw in that one photo from Australia, adjacent racks as well. And, basically that heat is just being transferred from or propagating just through the shells of the cells themselves. So that's one of the messages here. So how do we mitigate it? So we have water-based sprinklers. One of the pros with this is that water has a great heat capacity, so it really takes the heat out of the equation if you can get the water to the fire. It can help reduce the spread. It's water is very available and inexpensive, but it can cause problems as well because it can cause short circuiting in your electronic equipment, and also has the potential to generate off-gassing. And where you have these bulky things packed tightly together, it's challenging to get water into where the fire is. But we found that water mist systems seem to be the best. And there are chemicals that you can add to water, sort of surfactants or gelling agents that can improve the suppression capabilities of water. Then there's inert gas or clean agent systems. One of the main pro for this is that you can penetrate into deep-seated fires that are inside, where the components are tightly packed. One of the problems, though, is it doesn't have the cooling properties that water has, and so you're not pulling the heat out of the equation. And then these may also have the potential to form secondary toxics or corrosive products, further damaging. So what do? And basically the thrust of Rashawn's paper is that you're going to need to use some sort of multi-layered approach. You're going to want to kind of view it on a case-by-case basis, consider using fire in addition to the gas agents, but you're going to want to use things like detection equipment to make sure there's a fire going on and you're starting to respond to it, and then use a suppression system that aligns with a sort of an emergency response philosophy. So you have to think about, like, how is this fire going to be responded to? And then you're going to have to address any issues with that off-gassing. So this is the next section. This is where we're going to talk about what are the consequences if you can't mitigate, put out the fire. What happens after that? And so this is sort of like a little image of a flow chart of how the failures propagate into consequences. But so we've talked about the different hazards. We have the flammable materials, we have the electric potential, the potential for runaway, and the potential for off-gassing. And then we have some other aggravating factors. So we have a high energy density, a lot of capacity, and then we have this bulky format. So I think this is a good picture that sort of shows how bulky some of this stuff can be. This is an electric vehicle by Nissan, and so I want to show you this video, and I'm going to show it to you real quick, and I'm not going to talk, but then I'm going to ask some questions and then show it to you again. So bear with me. Okay, so I just want to focus. There's a bunch of questions here, but I want to focus on these three that are highlighted in orange. So one is, how long did it take to ignite? And I know that was kind of a chopped up video, but think about how long it took from that cloud starting until it was ignited. And then, was this a pre-mixed or a diffusion flame? And basically what I'm asking is, was the cloud that was coming out of the batteries, was it a pre-mixed cloud, or was it a well-mixed cloud, or was it sort of a gradient of concentration? And then another thing to think about is, what would happen if this event had happened inside of an enclosed building rather than out in a parking lot? So let's watch it again, and let's think about these 3 questions. How long did it take to ignite? Was it mixed or a diffusion flame? And what would happen in an enclosed space? And if you guys want to sort of like answer in the comments, I can't see those, but feel free to if you like. So we'll watch this quickly again. Okay. I don't think I can see the questions, but so basically my answers to these questions are, it did not take long to ignite. It happened almost right after the cloud started. And I would argue that this, the flame or the gas mixture was a diffusion flame. So later when you sort of, right once the bus sort of the flame engulfed the cloud, at this point you kind of have a flamethrower effect from the gases that are being thrown from the battery. So that's a more of a diffusion flame. And then what would have happened if this battery had been in an enclosed space instead? I think we would have had a much more dramatic explosion. So we're going to talk a little bit about what the different cases, so the sort of the initiating scenario, and then what happens if you do have a diffusion or a premixed flame, and how those mixture characteristics can cause different types of fire events. We're going to look at some of those fire events, and then how all of these have these effects that we're talking about. So, which are structural effects, thermal effects, and toxic effects. So, I think these are. I got a series of videos here that I want to show you, just to show you kind of what these different events look like, and why they're different. Basically. So this is a propane jet fire, and this has got this is at our test facility in, I believe this is the one that's out near Uvalde, Texas, actually, our Box Canyon test facility. Okay, I'm being told that there's a gray box or some pop-up that's interfering. Bear with me. Minimize this. I don't know what it is. Bear with me, we're just dealing with a little technical difficulty here. Okay. Can everybody see my entire screen? Okay. Hopefully you guys get the idea. I'm sorry about the technical difficulties. Please make a comment in the comment or in the chat if you have any, if you, for some reason, you can't see the entire screen. So what we saw before was a jet fire. And so basically this is a kind of a flamethrower. We have a release coming out of a pipe, and you have a pressure, a concentration gradient. As you're coming out of the pipe, you're pure gas and you're very rich. And it's not until that the air can sort of entrain into the jet, about here where this flame is ready to ignite that jet. And then beyond that, you have a much leaner concentration. And so you're able to have a fire. So now we're going to look at two different events. One is a flash fire and the other a vapor cloud explosion. Okay, so there was a flash fire on your left, a vapor cloud explosion on your right. So both of these basically, I believe, have well mixed or pre-mixed concentrations. And the main difference between the two of these is that in your vapor cloud explosion, you have an enhancement of that combustion rate, or because due to all the congestion, and you can kind of see a bunch of pipes and things in here, and so it increases the magnitude of the blast. And finally, we have a video that demonstrates fragments and drag loads. And this is unfortunately only a slow motion video, but it's pretty demonstrative. So what's going on here is you sort of have something similar to your flash fire or maybe your vapor cloud explosion setup, but in this case, you've enclosed the structure with these panels. And so when the fireball occurs, these panels are thrown and you've got the drag loads in the vicinity of the release. So so that's sort of, I hope kind of answers that question of what would happen if those buses had been enclosed in a garage or something like that. So now, so basically, when we do a consequence-based study method, we basically want to define the scenarios and talk about the potential battery hazards. We want to understand the chemistry of the gas and define something that's credible, maybe something that's slightly conservative but not too conservative. And then that's going to be our definition of our scenario. Then we're going to model what those effects are. So we're going to quantify, if we think it's going to be a jet fire or a vapor cloud explosion, what are the properties that we need to know for the combustion properties, and we want to assess those effects. And then we want to understand, and this has structural effects in the third element, but we want to understand what the sort of the consequence is going to be on the targets or on the receptors. And then so those can be buildings, which is the way it's phrased here, but it can also be just people or equipment or something like that. So we're going to look at the resistance of those receptors to the blast loads, the thermal loads, and toxic loads. And then we want to understand what do those results mean. So we want to, we're going to communicate this in sort of radiation contours, overpressure contours, the damage to the building, and then the vulnerability to the occupants of the building or people standing outside near the event to those loads. So once we have gone through that, what are our options in terms of sort of containing these hazard consequences? So this was my paper, and this is a very abbreviated version of it. But basically, we've discussed our hazards and concerns. So, you know, we have blast and thermal hazards, which are sort of both illustrated on this still frame here of an explosion that's impacting this pre-engineered metal building. And we also have toxic gases. And this is sort of a screen clip from some software where we're modeling the dispersion of a toxic gas and how it impacts buildings. So we've talked a little bit about our methods for load prediction. I'm going to go ahead and play this video. And so this video is basically a CFD prediction of a release of a toxic cloud, or a flammable cloud rather, in an enclosed building at the vehicle crash test facility for an electric vehicle manufacturer. So we have blast loads that we can determine with various methods for an enclosed space, such as a BESS. You have your NFPA 68 methodology. For open areas, if you have like a vapor cloud explosion, just in a large open area, you have your Baker-Strelo-Tang methods. And then we can use CFD to do various parts of that, the dispersion, the release, or even the thermodynamics. So this happens to be the FLAX, which can do thermodynamic computations. For thermal loads, you have NFPA 68 also. And you can also use CFD to figure that out. And then for toxic loads, fairly standard. You have modeled your release, your dispersion, and then we can also do infiltration rates into buildings. And then we want to determine what the human exposure, or the concentration versus time is. So how do we know if if the answer is good or bad? And so what we have is response criteria. And we have response criteria for various different kinds of hazards: the structural, the thermal, the toxic gases. And we have them for the various receptors, such as, you know, the buildings, the people, or the equipment. I like to show this one because it really explains structural response criteria in a visual way. So this would be for a reinforced concrete wall. And these are some tests that we did at another test facility that's closer here to San Antonio. But these are reinforced concrete panels that have a low damage, where you see some cracks that have been highlighted with markers here. A medium damage level, where you can tell that there's a little bit more cracks, and some deflection in this panel that you can see based on how it's separated from this butt frame. A high damage level, where you have sort of the same number of cracks, but your deflection is much greater. And then finally, a failure, where the entire specimen has fallen out of the test buck. We can also look at thermal criteria. So this is again for structural, but it's just an example. So we know that steel, when it gets to a certain temperature, begins to weaken. And this is just an illustration of different kinds of steels and how their temperature affects how strong they are, basically. So that's one criteria that we can use. Another is sort of the fire ratings of materials. So this is the ASTM E119 time and temperature curve, and this is sort of an idealized curve that models how temperatures rise due to like a standard building fire or a cellulose stick, which is a wood or paper fire. And basically it says, you know, how long does something last in the fire that goes from 0 and increases at this temperature curve? And this is how you get your, you know, a 90-minute door, or a 2-hour door, or you know, a 2-hour or 3-hour firewall, that sort of thing. So we can compare the predicted temperatures and times to these ratings and see if that's going to allow us to, is the answer good or not, basically, to understand that. And then we have various mitigation approaches. So for structural analysis, we use dynamic structural analysis. We can use finite element modeling. And so this is a nice picture of a large pre-engineered metal building that's being subjected to blast loads. We can design deflagration vent panels for buildings to decrease the loads inside of a building. And that's part of the NFPA methodology. For thermal loads, we can look at fire protection, material selection, or standoff distance if we're concerned about a target that's not part of the enclosure itself. And then for toxic gases, depending on what the scenario is, you can look at infiltration testing, gas detection, or shelter-in-place design. So this is the last section, and we're basically going to talk about, if these failures escalate and propagate and sort of consume, and don't get mitigated, what are the sort of risk management considerations? And so we're going to talk a little bit about, insurance risk and those types of things. So as we've talked about, we have multiple layers of protection. A couple things we haven't really talked about is the design itself of not just the batteries, but like the system. So we have some things that we can use to kind of reduce the potential for an event starting in the first place or escalating or cascading. And so we have battery management systems. So this is sort of detecting the voltage and monitoring charging discharge rates. And it can basically isolate a cell that has any behavior that's sort of out of the normal behavior, and prevent, maybe thermal rate runaway from initiating or propagating. Also, you've got your gas detection and things like that, so that you can begin sort of an emergency response once something started, and not have to wait till you've propagated throughout an entire BESS. So if something's already happened, though, you need to have kind of an emergency response plan. So your responding agencies, whoever that is, needs to understand what are the potentials. They need to know how bad could it be and what's the best way to fight that fire. And again, we can talk about explosion relief panels, and then an important thing that we've seen, like specifically for this Australia event that we've seen a few pictures of, is sort of the layout or separation distance. So this is just sort of a bow tie diagram. So you've got your causes over here that can cause thermal runaway. You've got your barriers that can prevent it from occurring in the first place, which is your design, your BMS, possibly gas detection and isolation. But say you've gotten through those barriers and you have a thermal runaway event that's cascading, propagating. You still have some things. You've got some, structural mitigation or explosion mitigation, fire protection or fire mitigation. You have your emergency response plan. You have equipment separation, and then you can sort of, you still have all these. If you get through all of those batteries, you have these consequences. And so the bow tie diagram is just kind of to show you where those barriers could be, and whether they're preventing the thermal runaway or dealing with it after the fact. So these barriers do fail occasionally, as we've seen in the incidents that we listed. And these incidents, lead to explosions and fires, which result in injuries and equipment loss. So our objective, of course, is to prevent injury to personnel, and prevent it from the hazards from escalating to damage further property. So what is sort of a worst case basis, or what is a sort of an insurance loss basis for one of these events? So I think you have to consider that the risk is that uncontrolled thermal runaway event will occur at some point. And if that happens, if you're trying to think about your sort of maximum loss or worst case, you need to think that, or assume that all the racks in the container or the enclosure will be involved. And that possibly, if those containers or modules are too close to each other, it could propagate to one other container. So the total loss of a BESS container and its contents are a credible event. Even if you have fire protection, trained firefighters that are well versed in what's going on, it's unlikely that you would be able to salvage the contents of a BESS container. Now, everything's changing. Industries dealing with these issues. So this is probably a statement that might not even be true now, but for most of the equipment that's out there right now, I think it is somewhat true. So recognize that there's a potential for this hazard to spread to an unadjacent unit if the separation distances are inadequate. And also recognize that environmental damage and cleanup could be a major issue. So you would have the fire water contaminated with the electrolytes and the other stuff, and you would have to deal with groundwater courses and soil contamination. So some sort of secondary containment might want to be considered. So I'm going to summarize this quickly. We're kind of at the end of our time here, but in summary, we expect the BESS industry to grow, the size of them and the quantity of them in the near future. Okay. We're still learning from these failures. So we've had at least 7 notable events in 2022. But as I said before, if you read into those anecdotes or the articles in chronological order, you can see that first responders and people that are installing these, they're learning from these events that have happened in the recent past. Third, the cause of these battery failures can be determined. We can use our battery failure analysis and forensic techniques to help us understand why they fail. But the frequency data is very elusive. So it's very challenging to use a risk management approach because we don't really have the battery failure data. And the technology is constantly changing. So even if you had a perfect snapshot of what's going on now, it's going to be completely different down the road. Number 5, the hazards can be quantified. So again, I said at the beginning, if you take anything away from this webinar, understand that the industry can use existing and industry accepted methods to predict hazards and consequence for BESS systems, and we can then mitigate or work to mitigate those consequences. So, however, number 6, fire protection is challenging. You might have to use a multi-layered approach with different types of systems, and train your first responders. And then, but we have tools that we can use to employ mitigation that can reduce the consequence. So you can reduce your risk. You might not understand where your risk is, but you can reduce it because you can reduce your consequences. So we can design structures to resist blast, thermal, toxic loads, and meet the existing response criteria. So we're fortunate there. And then in terms of the risk management considerations, loss of 1 or even more BESS units is the potential outcome. So, and then additional safeguard barriers like battery management systems and emergency response plans can be used to either reduce the likelihood or the consequences. So how can BakerRisk help? So this is our plug here. We have a suite of services that sort of touch on a lot of the different aspects that we've discussed. So as we mentioned, we do battery failure analysis here in our lab. We can do incident investigation, forensics. We can characterize the materials of a battery. we can do frequency analysis if you have the data. We can help you understand and apply that data. We have a bunch of fire protection engineers that can help you with those types of questions. We can help quantify and evaluate the hazards. We can help mitigate the hazards. We've done several sort of siting evaluations for BESS sites. We do structural design, mitigation design. We've designed or helped design several battery testing or abuse testing laboratories. We have extensive experience in testing shelter-in-place buildings, so air tightness testing and evaluating shelter-in-place buildings. We've done a little bit of testing for batteries themselves, as well as sort of testing for fire protection of batteries. But we have a lot of testing facilities, and we do a lot of specialized one-off testing for, different clients for different needs. And so we basically can help you understand the consequence for renewable energy. And then we, as we mentioned, do insurance risk. So that wraps everything up. And I went a little long because of our technical difficulties, but I think now we're going to open up for some questions. So by all means, I'll do my best to address any questions you have.
Perfect, Gabriel. I'm going to go ahead and ask some of the questions that did come up during the presentation. And just as a reminder, if you have not already done so, please be sure to type your questions into the Q&A box in your control panel. So Gabriel, first question, what is the probability difference of thermal runaway between NMC or NMA chemistries versus LFP chemistry? We hear that LFP cannot go into thermal runaway from cells folks.
Well, so I think that the answer is I don't know what the frequency distance, the difference in frequencies are. I think that basically, though, from my understanding, and I'm not the the person that models the hazards, and I'm not the failure analysis guy. That would be Anibal Morones or Sean Berg. But sort of my understanding is, and I've heard similar things about the NMC or NMP technologies. I think that the answer, though, is twofold. I have heard that they are less prone to failure. And I've also heard that any of these batteries has the potential for thermal runaway. So I know that's probably not a satisfying answer, and I just don't know the answer basically. But I know that under the correct conditions, maybe it's temperature or what have you, any of these batteries is going to be able to go into thermal runaway. And we've just worked mostly with lithium-ion battery hazards and don't have a lot of experience with the newer, different chemistries, unfortunately.
Perfect. We'll appreciate that. What is the best mitigation of thermal runaway?
I think that you want to have a layered approach to any sort of hazard, but obviously, if you can prevent it from happening with the things that were in front of your bow tie, sort of like the battery management systems, the detection, etc. You want to have things like that in place. But if you have to mitigate, obviously your fire protection system has got to be designed properly, adequate to get the heat and do to extinguish the flames. But I think it's just got to be a layered approach. You have to have an emergency response plan so that you're not introducing more hazard by putting people too close to try to address a hazard. And once you've gotten to that emergency response, unfortunately, sometimes it's better just to let things burn out or whatever than to put people in danger. So but the point is it has to be a layered approach. But you can't discount how important fire protection is.
Great.
So.
Next question. Are battery off-gas materials themselves flammable?
Sure. And there's plenty of materials that are both flammable and toxic. So when you're talking about like a jet fire, so to be clear, if you have a battery that's in thermal runaway, and if you recall that first video that I showed where you had the thermal imagery video, and one battery would cause the next one. So when they sort of flared up, what you're seeing there is off-gassing due to the heat expanding the contents of that casing and breaching it. And and it's causing a jet of gas to come out, and that jet is flammable. But I think what you might be asking is, are they both toxic and flammable? And the answer is a lot of them are. But the question is it going to be consumed by the fire, or can some of it release and not be consumed? So if you'll recall the bus video where you had that cloud before it was consumed by the flame, something could have happened that might have prevented that cloud from being ignited, and if it had not ignited, very likely to be toxic gases in that cloud. And we've done a lot of studies where we've modeled the dispersion of these clouds and looked at the chemistry and the toxic effects. So I hope I'm answering the question you asked, but
yes,
I threw enough answer in there to probably satisfy you.
Okay, have a couple more questions. What is it about batteries that makes the hazards unique?
Well, I kind of touched on this, but I think specific, batteries in general, they have not only the potential for these thermal runaway hazards, they also have electricity in them. So that's kind of different. But as far as the thermal runaway events, you have all the ingredients in your battery to sustain those that thermal runaway. So it's challenging to mitigate, and fire protection is very challenging because you've got your fuel, your heat, and your oxygen or your oxidizers all intrinsically as part of the battery. And so and it's going to be there and available to the event until everything's consumed. So.
All right, thanks. Next question. I have read that lithium iron phosphate batteries are not as susceptible to thermal runaway as lithium ion batteries. So why shouldn't I just select LiP battery and call it a day?
Yeah, so I think this is kind of like the first question with a different technology. But I think the point is that all these batteries are susceptible to thermal runaway. And I think we don't really understand the frequency as an industry yet. And I've read those claims and I'm sort of on the fence. I think one of the reasons why they appear to be less susceptible is because they're not as common, but we don't know. And so I think until we understand frequency and risk, we have to just assume that we have to understand that these thermal runaway events are possible with almost any battery or that we know of. So they can still experience thermal runaway.
So this will be the last question before we conclude this presentation. How do you design structural mitigation for toxic gases?
So that depends on the situation. Really, it depends on what your receptor is. Is the receptor like the enclosure itself? In which case, I don't know that we would care, except that sometimes those gases can also be corrosive or something, so we might damage equipment, but there's not people in there. And then, or the receptor could be people that are just offsite, like an emergency response person. And so or it could be a building that's maybe an offsite building. So it's really just important to understand and quantify the hazard and understand what the consequence could be. So if you have a person that's just a first responder and you are concerned that there might be a cloud, you need to quantify that release, the dispersion, and understand what the concentration would be in what area, and what the consequence in terms of human exposure to that toxic could be. But in a building, you can you can design a building, you can evaluate it as a shelter in place, or just as, how good is this building for toxics? And so you can understand what the air tightness is by doing air tightness testing, tracer gas testing, or blower door testing. And then you can model, the HVAC systems and everything to really understand what's going to happen if that toxic cloud encounters and envelops that building, and what the consequence to the human occupants would be. But basically, you need to understand what the hazards are. So you need to, do that.
Great. Well, we thank you everyone for joining us today. If you have additional questions, we ask that you reach out to Gabriel directly. And as a final reminder, today's webinar will be posted to our BakerRisk website. And once the recording is available, you will receive an email from BakerRisk with the link. Finally, we ask that you complete the survey at the conclusion of this webinar. Thanks again, Gabriel, and to our attendees for joining us today. And we'll see you in September for our webinar to introduce an update to the BakerRisk Electrical Classification Software Package Hack Tool.